Greetings! Isang pagbati na puno ng kaalaman. Many physical phenomena in engineering can be described in terms of partial differential equations as we have learned in the past lectures. In general, solving these equations by classical analytical methods with precision and accuracy sometimes would be difficult if we are dealing with models that have complicated shapes or geometries. And it seems that using classical methods would be very much impossible. Nowadays, engineers use the finite element method to predict the behavior of engineering systems for both design and performance analysis. Today, we will be giving a short introductory lecture on the finite element method. Aside from the analytical techniques used in solving different problems, numerical methods are tapped for much more complex systems for us to have a relatively easier computation at a faster time or at a faster rate, of course, without sacrificing accuracy too much. And one popular numerical method used in engineering is the finite element method. So in a finite element method, the models which are governed by different equations, which in our case sometimes would be partial differential equations or even ordinary differential equations as a much simpler model, or linear equations, are solved by part in smaller domains called elements. And once these constituent parts have been solved, our goal is to assemble the whole domain coming from the equations or the results of the smaller domains in order for us to get an approximate solution of the entire problem. That's finite element method in a nutshell. Now, before the calculation of a model, the first step in obtaining smaller domains, as we have mentioned, is what we call discretization or meshing. Our goal is to generate a finite element mesh of the model. So in meshing or subdividing the model into smaller parts, we can produce 1D, 2D, or even 3-dimensional elements. And in the finite element method, it is important for us to be able to accurately decide the size of the meshes, because a finer mesh produces more accurate and more reliable results. Now, when we talk about domain discretization and FEM, it's important for us to be able to define several terms. When we discretize or when we mesh, well, our goal is to obtain different elements or different parts which we individually solve. And the different types of elements that we encounter in FEM would be one-dimensional elements. So one-dimensional elements are line segments, and we normally use one-dimensional elements when we are dealing with rods, beams, and trusses. Then we also have two-dimensional elements. Two-dimensional elements, the most notable shapes that we use would be triangular shapes and quadrilateral shapes, which may be regular or irregular in nature. And if we are dealing with three-dimensional models, we have three-dimensional elements in the form of tetrahedrons or prisms. So these are the elements produced by meshing. And of course, the finer the mesh, the smaller the elements that we obtain. And if you look at the element, so as we have mentioned, the basic idea of FEM is to divide the body into finite elements, connected by nodes. So the the points at the end of the elements, okay, over here, okay, these dots in the elements that you see here, or in the edges, or at the end of the lines, are what we call nodes. Okay? Now, these are some example of different models, engineering models that are solved using FEM, okay? And has different elements, or have different elements rather. In this case, we have here a frame, okay, wherein we use line segments as the one-dimensional elements. So in this problem, this first 1D problem over here, okay, the elements are labeled as numbers and encircled. Okay? So you can see a number of elements. I think we have around more than 30 or 40 rather, okay? Nearly 50 elements in this model, okay? 48 I think, if I'm not mistaken. And the ends of the elements, okay, where the elements are joined together, are what you call nodes. So those are the ones labeled by the numbers without being encircled. Okay? So another would be two-dimensional triangular elements over here. And you can see that there are parts wherein the elements are coarse over here. And there are parts wherein the mesh, okay, or the discretization would be finer. Okay? Primarily because if you have a finer mesh, well, you'll get a more accurate result, but the computing time would also be longer. So the tendency of engineers, of what those who solve using FEM do, is that we tend to use finer elements at critical points. Okay? And lastly, we have here three-dimensional brick elements. Okay. Now, what are the different advantages of the finite element method? Number one, first and foremost, it can model any geometry, be it very, very simple to very, very complex. Second, the model can be easily refined for improved accuracy by varying the size of the element and the type of the element. And specifically, it can handle different loading conditions and different boundary or different initial conditions. Now, what's the general procedure of solving FEM? As we have mentioned, the first part is to mesh or to discretize, such that if we subdivide the model into a finite number of elements, our goal then is to derive or solve and eventually solve the equations governing each of the elements. And of course, the equations that would be used in solving these elements would be dependent on the type of problem. Once we have solved the different elements, the equations governing the different elements, we now assemble all these small elements, put them back together to form the original figure, the original model, in order for us to get the solution of the entire problem. Okay? So just to show you a simple visualization of FEM, for example, just as an example, for example, take this square figure over here, okay? And let's say I want to solve the stresses governing in that plate, for example, or the deformations when I subject it to different types of load. My first step, as we have mentioned, is to discretize. Okay? So I have subdivided the model into several elements, but then again, what I can do is I can refine the mesh even more, okay, for my elements to be smaller and for me to have more accurate results. And even further, what I can do is make an even more refined mesh. Once I have already discretized or meshed, my goal is, again, to analyze each element. So in this case, I have a quadrilateral element, and the end of the square element over here of the quadrilateral element, you see the nodes. So these are the black dots. That's what you call the nodes. And generally, I mean, not always, but generally, all the nodes can displace in the X and the Y direction, generally. Some may not, depending on the conditions, but generally, the nodes are allowed to move in the X and Y direction, or even in the Z direction if we're dealing with 3D elements. Such that, for example, for any loading condition, let's say I subjected the model to a load, such that this element will deform as such, for example. So that's what I'm going to do for all the small elements, for all different elements. I'm going to solve for the stresses or the displacements of each element. After which, if I would be able to do that per element, my next step is to assemble all the elements and go back to the original model and combine the results from my elements. Of course, I combine them using the governing mathematical equation, partial differential, ordinary, or any other equation that is governed by the model that I am, or the problem that I am solving. Then I should be able to get a solution for the entire problem. That's basically what FEM is all about. Let's try to look at a simple example of FEM. For example, we want to estimate the circumference of a circle. We know that the analytical solution of the perimeter or circumference of a circle is 2 pi r. So again, what we do in order for us to find the perimeter using FEM, first step, as we have mentioned, is to discretize. And in this case, I'll be using elements, one-dimensional elements, which are line segments. So for example, this here is what we call an element, which is a line segment. And at the end of the element are your nodes. So this is node 1 and node 2. So what I can do is, I have one element over there, element A. Then, again, I just mesh or discretize the entire circle using line segments, such that this is now my meshed or my discretized model. And again, as you may conclude, the finer the elements, the more accurate or the nearer the solution is to my analytical solution. After I have discretized, what I'll do, as we have mentioned, is just to look at one element and to solve each element one by one. So by geometry, I won't dwell into the math. I just like to go over the steps used in FEM. So we should know using geometry that the length of this element, h sub e over here, would be equal to 2r, where r is the radius of the circle, sine theta over 2. So theta is this angle over here. Now, that would be the governing equation for the element. After I have already obtained the behavior of each element, what I'll do is I'll assemble and I'll combine. But I know that the perimeter here is just the sum of the individual lengths of the elements. So it's just the sum of the length of each element. Hence, once I now get the sum of all the lengths of the elements from the previous step, I can now obtain the circumference of my circle. So that is your finite element method again. But most of the time, we need to impose what we call boundary or even initial conditions for different problems, because our engineering problems are actually unique, and your boundary conditions may be defined in accordance to the simplest one would be your support reactions. So this is where my statement earlier comes in, wherein I mentioned that generally nodes can displace in the X or Y direction, but not always. Why? Because, for example, if I have a boundary condition such as a roller, right? Well, I should know that the movement or the displacement is only along one direction. Similarly, if I have a boundary condition, let's say, which is a pin, I know that that cannot displace in the X or in the Y direction, right? So I can always impose my boundary conditions, right, to my elements or to my nodes for that matter. Now, what I'd like to show you here is how discretization happens. So in real life, there are different softwares that can be used, finite element method softwares that can be used, that are readily available, that can easily discretize your model. Okay? However, if you are hard coding, meaning if you write your own code, which you can do in the laboratory, or which you should do in the laboratory, you can hard code your model using, let's say, the simplest. You can code using C, the C language. Then, once you hard code, you can place it into, or input, serve it as input into an independent software to be able to discretize the entire model. Okay? So there are independent softwares such as Gmesh, okay, that can be used to discretize your model. But a lot already have built-in discretization processes. Okay? So our next few slides would be an appreciation of FEM in civil engineering. I'll be showing you examples of where we normally see FEM and where you can use FEM. Maybe later on, you can join us in the computational geomechanics team or the soil structure interaction team, where we develop researches concentrating on finite element method. Okay? So this would be, I think, a simple application that you will notice, or that you know. This is buckling of a column. So the buckling of the column can be modeled using FEM, wherein our goal in this case is to obtain the displacements and the stresses in each point in the model as your load is being applied and as the column buckles. So this is for structural engineering. In geotechnical engineering, we can also model the behavior of the soil underneath the foundation, such that, for example, if I have a uniformly distributed load over here, and I apply this load, my soil can deform as such. And using your finite element method and by discretizing this model, I can come up with a contour plot of the displacements of the soil at different nodes or different points. And of course, initially, the displacements and the deformation of different elements comprising this entire model. Another in geotechnical engineering, but in this case, I think I'm showing you here a three-dimensional meshing, a three-dimensional model. We analyzed the behavior of the stresses and the deformation of soils underneath closely spaced foundations over here. So you can see we used three-dimensional tetrahedrons as the elements over here. And on the right-hand side would be the results coming from one of the test cases. And in the field of transportation and geotechnical engineering, given different dynamic loads, you can model this distributed load as a moving load, as a car, for example. We should be able to use finite element method in modeling the embankment and the road, and consequently the stresses and the deformations for each part. And for C28, we will be solving trusses. So later on in the succeeding lectures, you will see that the finite element method can be used in solving the internal forces, which you have learned in your static subject, and the stresses, which you have learned in your mechanics, engineering mechanics or mechanics of deformable bodies subject, and right, the deformation and the displacement of the nodes which you have solved using your advanced right, mechanics of deformable bodies. So all those three, support reactions, internal and internal forces, right, stresses per member, and deformations or displacements can be solved using finite element method. So I hope you were able to appreciate finite element method as a technique in solving complex problems, right, in engineering. Until our next lecture, thank you.